Hello, today we are going to study how it is possible to design and model concrete elements taking into account the contribution of polyolefin fibers. In the image that can be seen in the slide, the improvement of the mechanical properties of concrete when an hypothetical amount of polyolefin fibers is added can be seen. In the gray line, the mechanical behavior of a plain concrete without any reinforcement subjected to a 3-point bending test in a notch specimen can be seen. As has been previously explained in other lessons, the load deflection curve is mainly linear up to the peak load is reached. Afterwards, an unloading branch starts, having a quasi-brittle behavior until the total unloading of the sample. However, in the case of the polyolefin fiber reinforced concrete, the influence of the fibers is negligible in the loading branch. However, in the unloading branch of the polyolefin fiber reinforced concrete, the load decreases until reaching a minimum. After this point, the load-bearing capacity of the material increases and a post-peak loading branch starts. This branch ends after reaching the maximum post-peak load, where an unloading starts at a slow rate. In order to take into account the contribution of the fibers in the structural design, some recommendations have been developed. The most relevant in Spain are the model code published in 2010, and overall, the Structural Concrete Design Code, EH08. In this recommendation, the behavior of the material that was registered in the test as load crack opening curves is transformed into stress crack opening curves by using the equation that is derived from theory, assuming that the concrete central section is able to withstand stresses throughout the test. As an example, the model code considers an ideal stress crack opening curve. If the contribution of the fibers can be taken into account, in the structural design there are two conditions that should be fulfilled. Firstly, the stress value at 0.5 mm of crack opening should be greater than 40% of the one registered at the peak load. Secondly, the stress value at 2.5 mm of crack opening should be greater than 20% of the one registered at the peak load. In the case of EN 14889, the contribution of the fibers can be considered if the stress value at FR1 is greater than 1.5 megapascals. In the case of PFRC, after more than 100 tests performed in plain concrete, reinforced with different contents of fibers, which range from 3 to 10 kilograms per cubic meter, the following remarks can be concluded. It was possible to meet the requirements set by the model code at the EH using polyolefin fibers. Moreover, using 10 kilograms of fibers, all the requirements were fulfilled in all cases. All the amount of fibers used, including the lowest contents of 3 kilograms, were capable of meeting the requirements at crack openings of 2.5 millimeters. With 6 kilograms of fibers added, the behavior of the concrete was in the limit for considering the contribution of the fibers in the structural design. In addition, the stress value for 3.5 millimeters of crack opening were greater than those found at 2.5 millimeters, so the ultimate stress limit was exceeded in all cases. Moving to modeling the mechanical behavior of polyolefin fiber reinforced concrete, it has to be said that traditionally some of the most used softening functions applied to fiber reinforced concrete have been built by joining straight lines with several slopes. Up to now, the main differences between were established in the second zone, which differ from a slope 0 to a negative slope. The central part of the softening functions did not comply with what was observed in the case of polyolefin fiber reinforced concrete test. Therefore, a modification of the slope of this central part was carried out. Instead of having a negative slope, in order to reproduce the mechanical behavior of polyolefin fiber reinforced concrete, the central part of the curve should have a positive slope, as can be seen in the image. The accuracy of this approach was proved by means of numerical simulations. Using the data extracted in the compressive strength test, the modulus of elasticity test, and the indirect test, and supposing a trilinear softening function, the complete behavior of the material could be checked. In order to perform this task, the material behavior was implemented in a commercial finite element software, using an user material subroutine. After the numerical calculus has been performed, the experimental behavior and the one obtained in the calculus was compared. If the fracture energy and the behavior are not comparable, the parameters that define the material unloading are modified. Once modified, the new behavior is implemented in the numerical calculation performed again. This process is repeated iteratively until a similar properties and behavior is obtained. This iterative process is based on changing the values that define the characteristic points of the three linear softening functions. Among them, the most important ones are those that define the minimum strength in the unloading branch and the maximum post-peak strength. By changing the values that define these points, the following results were obtained. Modifying these characteristic points, the behavior of PFR with 3 kilograms, 4.5 kilograms, 6 kilograms, and 10 kilograms of fibers could be reproduced with great accuracy. The constitutive relations of such formulations can be seen in the image. The image start of the reloading branch in all formulation changes as could be expected. The greater amount of fibers, the higher onset of the reloading curve. Similarly, it can be clearly perceived how the slope of the reloading branch increases as the amount of fiber grows. It has to be pointed out that the point of failure of the material is the same and does not depend on the amount of fibers added. But apart from defining the softening functions in the cases of adding 3, 4.5, 6, and 10 kilograms of fibers, the most interesting part would be to establish the functions that relate the minimum load in the unloading branch and the maximum reloading value in terms of the amount of fibers added. In order to find this function, the slope of the straight line that connects the origin of the graph of the softening function with the minimum load in the unloading branch has been related with the volumetric fraction of fibers in the 4 cases studied. By performing this graph that appears in the right part of the slide, we can see that there are an exponential function that fits with great accuracy the experimental data. Regarding the maximum load in the reloading branch, the values found were related with the volumetric fraction of the fibers, the orientation factor, and the ultimate stretch of the fibers, and the amount of fibers that were pulled out. It was decided that a linear relation among all these parameters were the best option to having a remarkable accuracy. Using these two functions, the values of the minimum load in the unloading branch and the maximum load after the peak load, the softening function of any amount of polyolefin fibers added could be obtained. Thank you for your attention.